In this video, I'm going to do an example where we calculate the KSP value of a salt given molar solubility. And I'm going to demonstrate two methods that can be used to solve these types of problems. So, the example that we're given, in this example, we're asked to calculate the KSP value of copper sulfide at 25 degrees Celsius if the molar solubility of copper sulfide at this temperature is 8.89 times 10 to the negative 19 moles per liter. So in the first method, we're going to use an ice table to solve this problem. And this is the dissociation, this is the equilibrium that's formed when copper sulfide is placed in water. We get a copper 2 ion and a sulfide ion. And the equilibrium expression will be the product of the copper 2 ion and the sulfide ion. So of course, when we initially place this copper sulfide in water, we're going to have an initial concentration of 0 for both of the ions. And we'll have a change in concentration equal to plus x. And I didn't write it down, but we know that x is equal to the change in concentration of the copper 2 ion, which is equal to the change in the concentration of the sulfide ion. So that at equilibrium, we have a concentration of x for both of the ions. And we know from our equilibrium expression that the KSP value will be equal to x squared, because the concentration of both of the ions is equal to x, and therefore combined they're equal to x squared. And we know that x is equal to the molar solubility of copper sulfide. And this is because at equilibrium, the concentrations of the ions are equal to 8.89 times 10 to the negative 14. That is what molar solubility represents, the concentration of the ions at equilibrium. And just as an added note, when we do this calculation, we know that we're going to get a very small KSP value, simply because the molar solubility is incredibly small, meaning that the left side of the equilibrium is favored very much. So that's also something to look out for. And this ends up giving us an answer of 7.90 times 10 to the negative 37. And then the second method that I'll demonstrate involves a little more algebra. And in this type of problem where we have a 1-to-1 ratio between the ions and the solid, an algebraic method will probably be much faster to use. So we know that the concentration of the copper ions is equal to the concentration of the sulfide ions, which is equal to the molar solubility of copper sulfide. And therefore, we can actually rewrite the equilibrium expression as being equal to concentration of the copper ions times the concentration of the copper ions, because the concentration of the copper ions is equal to the concentration of the sulfide ions, which of course is just equal to concentration of the copper ions squared, which is the molar solubility, which gives us the exact same answer as above. Now this method is, as I said, is useful when you have like a 1-to-1 ratio between the ions and the solid. But when you have ratios that are not 1-to-1, then I would definitely recommend using the first method, using an ice table.